Now we're going to do a slightly more complicated problem to do some calculations with Newton's second law. A sled is pulled by a rope that connects with the sled at a 35-degree angle. When I wrote this, I should have said 35-degree angle off horizontal. The pulling force is 90 newtons and the sled has a mass of 18 kilograms. Stop, picture time. So here's the sled. It's getting pulled by a rope that connects with the sled at a 35-degree angle. Now here's the ground. That 35-degree angle is meant to be right there. That's what these problems usually mean, like connecting with it at a 35-degree angle. You should assume, if it doesn't say anything else, that it's a 35-degree angle off the ground. Okay, we've got a 90 Newton force pulling in that direction, and the sled has a mass of 18 kilograms. We're going to see why that matters in a minute. First of all, explain why the sled does not lift off the ground. Well, look at what would happen to make the sled lift off the ground. Under what circumstances would it lift off the ground? It would lift off, it would lift if the upward force were greater than the downward force. So now we have to go and find out why this is not going to be true, why the upward force is not going to be greater than the downward force. For this, it matters that the mass is 18 kilograms because that determines the strength of gravity's pull on this object. In case you don't know, the force of gravity acting on something is always equal to its mass times gravitational acceleration of 9.8. So this will be 18 kilograms times 9.8. And that is 18 times 9.8, 176.4. This is the force with which gravity keeps the sled on the ground. If there is an upward force that exceeds that, then the sled will begin to lift off the ground. But in the absence of such a force, the sled will stay on the ground. So let's now examine what could possibly be supplying any upward force. Like, things don't spontaneously lift off the ground. The only time that it makes sense to ask whether they're going to lift off the ground or not is when there's something that's pulling them up in the first place. And then you say, well, is it strong enough to lift them off the ground? Why is there something lifting it off the ground? Here's why. See this thing right here, this 90 Newton force? That is not just pulling the sled along the ground. It's pulling the sled at an angle. And at an angle, the sled is being pulled both horizontally and vertically. To figure out how much of the pull goes each way, we have to split it into components. So split 90 newtons at 35 degrees into horizontal and vertical components. We've got a nice juicy right triangle right here, where the hypotenuse is the 90 newtons. The vertical leg right here, that is going to be determined by trigonometry. And the horizontal leg, this is the thing that pulls it along the ground, is likewise going to be determined with trig. So let's call this Fy and this Fx. If you know your trig, which I'm guessing you do, you probably know that the sine of a 35-degree angle is equal to Fy over 90. Yes? Yes. Heads nodding. Yeah. Fy then is equal to 90 times sine of 35. And using handy dandy Mr. Brain, I can say that that is equal to 51.6. It is a force, so I'll label it with newtons. Here, I have the upward force on this object. So Fy equals 51.6 newtons. Now, at this point, you would be right to criticize me for sloppy labeling because I've been a little bit loosey-goosey with the minus signs. Let me go fix that. This 9.8, because it's pointing down, I will assign it a negative sign. That will cause this to be negative, which is going to be more honest than the way it is right now, because if this is negative, it makes sense for this to be positive, because the positive points up, the negative points down. So let me fix that. Minus, making this minus, and now all is well with the world. Explain why the sled does not lift off the ground. Well, Mr. Physics Problem, I'll tell you why it doesn't lift off the ground, if you'll allow me to type for a minute. The sled does not lift off the ground because the vertical force from the rope is only 51.6 newtons compared to the 176.4 newtons downwards supplied by gravity. Because the upward force from the rope is not as large as the downward force from gravity, the sled stays on the ground. Simple. Okay. Now, more computational. What is the horizontal acceleration of the sled? Horizontal acceleration is determined by, guess what? Our good friend F net equals ma. Okie dokie. Well, let's see. Horizontal acceleration. Remember that when you look at acceleration, it always needs to point in the same direction as net force. So, net force equals ma. Have we figured out the net horizontal force? We're going to apply this equation just to the horizontal. What is the horizontal force on this? Or I'll say the horizontal net force, because there may be more than one force. We've got Fx, which pulls it to the right. And then is there any force that pulls it either to the left or additionally to the right? You should be able to decide here that the answer is no. There are no additional horizontal forces. Sometimes you need to be on the lookout for friction, but this specifically says that we can ignore friction, so we don't have to worry about that. So Fx is the entire net force. That means that calculating Fx will give us the net force. Calculating Fx is a matter of taking the cosine of 35, and that'll be Fx over 90. So Fx is 90 times cosine 35, or let me see about this. Cosine of 35 times 90 is 73.7. That is a force, so it'll get labeled with newtons. And now F net will equal ma. Now we use the fact that the sled had an 18 kilogram mass before when we calculated its force of gravity. Now we're going to do it again, because now if net force equals mass times acceleration, we can put in what we know and solve for what we don't. 73.7 newtons equals the known mass of 18 times the unknown but soon to be known acceleration. Divide by 18 on both sides, 73.7 divided by 18, and that is 4.09 meters per second squared. So what is the horizontal acceleration of the sled? It is exactly that, 4.09 meters per second squared. And you can say in the same direction as the rope is pulling, the rope pulls along the ground. In case you think the person correcting this thinks that you're an idiot and might think that it's going to accelerate in another direction.